Okay, so in the past chapter, we have learned how LDPC codes are defined, and we have also seen how we can optimize the parameters of LDPC codes. We have seen how to analyze LDPC codes in the case of regular codes. We have seen irregular codes. Now we would like to construct codes and see how they actually perform when we simulate the performance of those codes. And this is what we start with. So we are going to look at a few aspects. First, we're going to see how we can construct actually irregular codes. For regular codes, we have seen Gallagher's construction. And for irregular codes, we're still missing how to properly construct such a code. And then we are looking at the error approximation, and we're going to calculate actually analytically how to approximate error performance. And finally, we're going to see how to improve the error performance to get something that works practically. So let's take a look at how we can construct irregular codes. So here's the blueprint of how we proceed. The first thing is we fix the length of the code, n. So for instance, recall the challenge. We were given to construct a code of a specific length n. This is usually given by some framing, by system designers. This is something that you usually cannot fix by yourself, but that's given by some upper constraints. And then we have some degree distribution polynomials. For instance, we have lambda of z and we have rho of z. And we have n, and in order to construct the code, we need the polynomials capital lambda of z and capital P of z. So how do we get those? Well, recall that what we have lambda of z and rho of z, they are usually given, and we know how to calculate capital lambda of z. So first thing we do is we calculate capital L of z. Capital L of z is given by the integral from 0 to z of lambda tau d tau divided by the integral from 0 to 1 of lambda tau d tau. And then we get capital lambda of z equals n times L of z. L of z is the normalized version, and capital lambda of z is the non-normalized version. And very similarly, we get R of z is equal to the integral from 0 to z rho of tau d tau divided by the integral from 0 to 1 rho of tau d tau, and then we get P of z or capital rho of z is equal to m times R of z. Okay, so that's the first step that we're going to do. So now the second step is we pick n variable node, or we place n variable nodes. And we know that n is equal to lambda of 1. So and then we assign to each variable node of degree I the total number of I sockets. So we have a variable node that is of degree I, and we put a socket to each variable node. We can think of a variable node was a circle, and this circle has some sockets. And we have, in this case, we have a degree 3 variable node. So we put 3 of those empty sockets here. So it's just a socket like a power outlet, like a socket where you can put in a cable or a plug. Then we do the same thing for the check nodes. So we put a check node. And again, for the check nodes, we put some empty sockets. Again, we put m check nodes, and we assign to check node of degree I a total number of I sockets. So now we have variable nodes. Each of the variable nodes has a number of sockets, and the total number of sockets is E. And E is lambda prime of 1. And we just label each socket with a number. So each socket gets a number. We start from 1 to E. The first socket is socket 1, socket 2, and so on until we reach socket E. We do the same thing for the sockets from the check nodes. We start labeling the first socket being socket 1, socket 2, up to socket E, and E is equal to lambda prime of 1, so it's the same E. We have the sockets must be identical, and this is also P prime. So, and then what we do is we select a random permutation of the numbers from 1 to E. And then what we do is we connect sockets from the variable node to the check nodes according to this permutation. So we connect socket 1 with the first socket after the permutation. Then we connect socket 2 with the second socket after the permutation. And then we just keep on doing this. Keep on doing this with the permutation. And at the end, we check if there are parallel edges. So what can happen is we can have one socket from a variable node to a check node. And we can connect the same variable node with the same check node again. This is not meaningful. And this is something that we need to break up. So we look and identify this, this fact. And if such a thing happens, then we need to swap the edges. So then we swap this edge with another edge now to resolve this parallel edge. That's the blueprint. That's how we're going to proceed. And let's take a look at how this works with an example. So we have a degree distribution, and we start with this degree distribution that we get from the optimization, for instance. So we have lambda of z is equal to 2 over 5 times z plus 3 over 5 times z squared, and rho of z is equal to z power 4. And now, again, a very good exercise is to do the calculation of L of z and R of z by yourself. So try to do this. So we get L of z is equal to 1/2 times z squared plus 1/2 times z cubed. And R of z is equal to z power 5. And then we fix n. So here we fix n is equal to 6. So if n is equal to 6, we just multiply L of z by 6. We multiply P of z by m. How do we get m? Well, m is given by the rate, by the design rate of the code. So we know that the design rate of the code, RD, is equal to 1 minus integral from 0 to 1 of rho of tau d tau divided by the integral from 0 to 1 of lambda tau d tau. So when we do this, we get the design rate. Design rate is 1 minus m over n. This is equal to 1 minus m over n. And then we can get m. We can resolve this for m. Okay, so once we have this, we have the degree distribution from node perspective, the non-normalized, lambda of z and p of z. So we see that we have 3 variable nodes of degree 2, and we put those 3 variable nodes, they have degree 2, so we assign 2 sockets each. So this is socket 1, socket 2, socket 3, socket 4, socket 5, socket 6. Then we have 3 variable nodes of degree 3. So we have these 3 variable nodes, and they have degree 3, so they have 3 empty sockets. And then we have 3 check nodes. They are of degree 5, so each of those has 5 sockets. 5 sockets, we have 5 sockets. So on both sides, we see that we have a total number of 15 empty sockets. And with these sockets, we can now get random permutation. So the next step is we fix our random permutation. So random permutation is this one. It's just a permutation of the numbers from 1 to 15. So it means that we connect socket number 1 with socket number 8. So this is 1, this is 6, 7, 8, and we connect 1 with socket number 8. We connect socket 2 from web node side with socket number 9 from check node side. This one. Then we connect socket 3 with socket 4. We connect socket 4 with socket 12. Then we connect socket 5 with socket 15. We connect socket 6 with socket 2. Now we are here. We connect socket 7 with socket number 1. We connect socket 8 with socket number 13. And we connect socket number 9 with socket number 6. Then we connect the next socket with socket number 7. Then we go to socket 11 and socket number 5, and so on. So we go to socket number 3, socket number 10, and socket number 14. Okay, so this is how we can do the rearrangement or the permutation. We see that we have two parallel edges. We have this edge and this edge. They connect both to the same web node to the same check node. So this is a situation that we need to resolve. This is what we do in the next step. So we have it drawn here in a more beautiful way. We have two parallel edges. So we're going to take this edge and we're going to swap it with another edge. So we're going to swap it with, for instance, we could take, for instance, this edge. So it means we connect this guy, we kill the connection here, and then we just swap those. So we're going to swap this one over here, and we're going to put this one over here. And let's draw it in the same color. So this could be a way to resolve the situation. We haven't introduced new parallel edges, so this is one way of resolving it. Another way of resolving it is shown on the next slide. That is by picking this edge, for instance. So I could pick, let me do it with this edge as well. You see that there is not a unique possibility, but there are multiple such possibilities. And let me just go back. So we could change it. This edge. Okay. So what we do is we erase this connection here. And we erase connection over here. And now here we're going to put this guy over here and this guy over there. And now we don't have parallel edges. So you just pick one edge that when swapping will not cause a new parallel edge, and then you just do the swapping of the edges. So this is shown here in the example as well. So we pick the blue edge here in the tenor graph, and then we just swap, and we finally get the code. So we then remove the sockets, and after swapping, we just draw the tenor graph. From the tenor graph, we can get, again, the parity check matrix, and this is our irregular code that we have just constructed. So you see it is pretty easy also to construct irregular codes and graphs of irregular codes. So there is an example also. So if you want to construct codes, we show first how to construct regular codes using this technique. So without irregularity. So just DVDC, regular codes, but the same techniques. All the variable nodes, all the check nodes, they have the same amount of sockets. And we have a MATLAB file called getRegularH. When you want to apply this technique to construct irregular codes, you will often face difficulties. And the difficulties are mostly due to the fact that when you have a degree distribution, you will not end up with such a nice degree distribution as we show here. Because here everything turns out pretty nicely, because what happens here is when you multiply L of z with n, you end up with integer numbers. In the real world, this is usually not the case. You usually have a degree distribution, you multiply with n, you don't end up with an integer number, so you need to do some rounding. And then you may have run into some trouble that the number of edges from variable node side and number of edges from check node side after rounding do not correspond. And then you need to do something else. You need to do some tricks, and we will see how to resolve these tricks. So the workflow, again, is the following. From the optimization, we know lambda of z and rho of z. We calculate L of z, R of z. As I mentioned before, you have the equation again here. Then we calculate lambda of z, E of z, and then we construct the nodes with the sockets, we construct the graph. So the problem that we encounter is that the coefficients of lambda of z and P of z are not necessarily integer. Particularly if you look at the degree distribution, we end up with something that may not be integer, and that could be an issue. So how can we get around this? Well, the way it works is that we need to modify L of z and R of z such that we will have integer coefficients after we multiply with n. So what we want is that when we calculate n times L of z and m times R of z, we should end up with some integer. So Li, which is the coefficient of the polynomial, should be something that can be written as pi divided by n. And same, Ri should be something that can be written as qi over m. So we should have some fractional coefficients, and therefore this is not necessarily the case. So what we do is we approximate L of z and R of z by tilde of z and R tilde of z, which have these fractional coefficients. So we introduce L tilde of z and R tilde of z. And when we multiply L tilde of z by n, and R tilde of z by m, we end up with integer coefficients. That's the main idea. And L tilde of z and R tilde of z should be close to L of z and R of z, and they should be close approximations of L of z, but they should fulfill this property. So how do we do this? So how do we measure being reasonably close? Well, what we want is we want L tilde of z and R tilde of z. They should be close to L of z. So we just minimize their distance. And the easiest thing to do is minimizing the absolute value. So we would like the sum of L tilde of I minus L tilde, the absolute value, should be as small as possible. So each L tilde of I should be as close as possible to L of I. And we measure this by just taking the difference and the absolute value of the difference. The sum of those should be minimum. And also the sum of R tilde I minus R I, absolute value, should be as small as possible. So This is how we measure the closeness. Then we should have coefficients Li. They should be coefficients. So they must fulfill some properties. First of all, the values L tilde I must be between 0 and 1, because they are still a fraction. They cannot go above 1. And the sum of L tilde I must be equal to 1. And the same holds for the coefficients R tilde I. R tilde I must be between 0 and 1. And the sum of R tilde I must be equal to 1. Okay, so we have a constraint. Then we have another constraint. So the number of sockets from the variable node side must be equal to the number of sockets from the check node sides. They must be the same so that we can connect all the sockets. So what is the number of sockets? Number of sockets is the sum over all i's n times L tilde of I. That's the sockets, the number of sockets of degree I. So here's the fraction of variable nodes of degree I. We multiply by n, so that's the number of variable nodes of degree I, and each of them has I sockets. We multiply by I. So this is the number of sockets, or the number of edges from node side, and this is the number of edges from check node side. So it's the sum over j. R tilde j times m is the number of check nodes of degree j, and each of those has j sockets. So we have a couple of constraints, and this means we can formulate an optimization problem. So this looks very similar to what we did when optimizing degree distributions. We had an optimization problem. It was that the exit curves should not overlap and the code should converge. Here we have another optimization problem. So we can formulate an optimization problem. So let's do this. So let's formulate an optimization problem. And what we do is we directly optimize lambda tilde. So we fix lambda tilde, and we define lambda tilde to be equal to n times Li tilde. And we fix pi tilde to be equal to m times Ri tilde. So it's the unnormalized degree distribution. So what do we want to minimize? We wanted to minimize the difference between Li tilde and Li, or the difference between lambda I tilde times lambda I minus lambda I. Doesn't matter how we do the normalization, where we do the normalization. So we have the sum over all degrees, lambda I tilde minus n times Li, plus the sum of all check node degrees, pi tilde minus m times Ri. And we sum up both of those objective functions, and we would like to minimize this difference. Okay, and then we of course have the constraints that lambda I tilde and pi tilde must be integer. So lambda I tilde must be an integer, could possibly be 0, so it must belong to n0. It's a set of non-negative integers. And pi tilde must belong to the set of non-negative integers. So, so it means that lambda I tilde and pi tilde should be integers and non-negative. Okay, so now we have everything at our disposal, and we can actually write down the optimization problem. And here it is. So here we have the optimization problem, and let's go through it step by step. So we would like to minimize our objective function. Objective function is what we have already described. So the sum over the different degrees of the absolute value difference lambda I tilde minus n times Li plus the absolute value difference of pi tilde minus m times Ri should be as small as possible. Then we have constraints. The lambda I tilde, they must be integers, non-negative integers. The pi tilde must be non-negative integers. Okay. The sum over lambda I tilde must be equal to n, and the sum over all pi tilde must be equal to m. The number of edges, so this is the number of edges, e is equal to the sum over I times lambda I tilde. This must be equal to the sum over I times pi tilde. The number of edges from variable node side must be the same as the number of edges from the check node side. Then we have some more constraints. We don't want to have variable node of degree 1. So we say that lambda I tilde 1 is equal to 0. We don't want check nodes of degree 1 and 2. So we fix pi tilde 1 is equal to pi tilde 2 is equal to 0. And we also fix that lambda tilde 2 is smaller or equal to n times L2. We don't want to introduce new degree 2 variable nodes because degree 2 variable nodes can be harmful. We want to keep them as small as possible because, to recall, the stability constraint defines lambda 2, and we may be just at the edge of the stability constraints, and by adding just one variable node of degree 2, we may violate the stability constraint. So we want to restrict the number of variable nodes of degree 2. This is our optimization problem, and this is not a linear optimization problem, but a convex optimization problem. It's convex because the absolute value looks like this. So this is the function, this is the absolute value function. That's a convex function. So the second derivative is always positive, and therefore it's a convex function. We can transform this optimization problem into something linear, and that can be done by introducing so-called slack variables. So if we want to optimize some absolute value of x, the absolute value of x means we have either have x or we have minus x. So what can we do instead? So we can optimize some value t. So we can minimize some t, and we fix that x is between minus t and t. So this is an equivalent formulation. Instead of optimizing directly the absolute value of x, we minimize the boundary of this interval. So we have this interval here, and we minimize the upper bound of this interval, and we say that x must be inside this interval. This is an alternative formulation. So for every absolute value, we introduce a so-called slack variable, which is called mu I for the first sum and nu I for the second sum. And then we can formulate an integer linear program. So that's shown here. So we minimize the sum over mu I plus the sum over nu I. This is clearly linear. Then we want the absolute value. We have the absolute value of lambda I tilde minus n times Li. So this guy is then contained between minus mu I and plus mu I. So we sandwich this guy with either minus mu I and plus mu I, and we fix just this upper bound of this interval. And by doing so, we equivalently minimize the absolute value. We do the same for the second sum. So p tilde I minus m times Ri must be sandwiched between minus nu I and plus nu I. And that's it. So the other constraints, they stay the same. And we also fix mu I tilde and nu I tilde to be equal to integers. They are not necessarily integers, but we fix them to be integers. Actually, we don't need to fix them to be integers at a second thought. So we could even get away with not fixing them to be integers. This is something we can provide software for solving this. It's something we can play around with, but actually we don't need them to be integers to be precise. Yeah, we don't need them to be integers. So that's something we can cross out. Okay, so let's how can solve this? Well, we can solve this using standard solver tools. You can do this using CVX, Py, and Python, for instance. There's support for integer programs. We also have this included in MATLAB, and I provide MATLAB code. So in MATLAB, it's called optim problem. And we have a file called dectist to integer, shows how this conversion can actually be done. So we can convert a degree distribution to an integer lambda I tilde and pi tilde using integer linear programming. So, and with this, we can also construct the matrix. So a few caveats. Integer linear programming is something that is known to be NP complete. So integer programming itself is extremely efficient. As soon as you introduce some integer constraints, it becomes something NP complete. So we don't have guarantees that we can easily find a solution. And for large dimensions, finding the solution can become extremely difficult. However, we have a rather well-behaved problem at our hand. Our dimensions are rather small, so we have very efficient numerical solvers that uses a lot of tricks to simplify the reduced search space, and will actually have a very, very good performance. So it's not a big problem for the problem we are looking at. So we have a very efficient way of solving these things. Okay, so here we also provide an example of constructing an irregular parity-check matrix from lambda of z and rho of z, and this is called get irregular h. So we also have in the description of the file, you have an example for one irregular code that we saw in the lecture. Okay, so that's it. So with this, we can now construct codes, and having those codes, we can start simulating. So we can construct a parity check matrix from the irregular code. You can do your simulations. So essentially, for the challenge, you now have everything at hand. You have a complete workflow. You can now generate a degree distribution. You can generate an irregular code, and you can generate a matrix. So rather encourage you to try constructing a code with the for the rate and the length n that is given by the challenge, and to play around with the parity check matrix, simulate the parity check matrix a bit, and see what you can get. So what we'll do next is we're going to actually simulate some codes and see what is going to happen and how we can work around with the errors that we will observe and that are bound to happen in this case. So with this, I will pass on to the next video.